This paper explores the intersection of quantum computing, advanced mathematics, and information theory. We delve into the fundamental building blocks of quantum computation, exploring the unique properties of qubits and the operations that can be performed on them. Specifically, we examine how quantum states can be represented as vectors in Hilbert space, allowing us to utilize the tools of linear algebra and quantum operators for manipulating and transforming these states. We then delve into the world of quantum algorithms, examining their power and potential for tackling problems intractable for classical computers. Classical bits, the building blocks of traditional computers, are limited to representing a single value at a time, either 0 or 1. This binary nature restricts the information that can be stored and processed by classical computers. In contrast, quantum bits, or qubits, exploit the principles of quantum mechanics to achieve a significant advantage. Qubits can exist in a superposition state, simultaneously representing both 0 and 1. This allows for the encoding and processing of exponentially more information than classical bits. Imagine a coin spinning in the air, not yet settled on heads or tails. This represents a qubit in superposition. This capability, known as quantum parallelism, empowers quantum algorithms to perform computations on a vast number of possibilities simultaneously. This inherent parallelism promises to deliver exponential speedups for certain computations, making quantum computers potentially far more powerful than classical computers for specific tasks. For example, Shor's algorithm can factor large numbers exponentially faster than any known classical algorithm, which could revolutionize cryptography. Quantum operations are performed by applying sequences of unitary transformations, known as quantum gates, to manipulate the superposition states of qubits. These gates act like logic gates in classical computers, but with the added ability to manipulate superposition and entanglement. Unlike classical logic gates, which operate on bits in a deterministic way, quantum gates can create entangled states between qubits, allowing for non-local correlations and complex computations. Think of two coins flipped simultaneously, landing on the same side. That's entanglement. These entangled states are essential for realizing many powerful quantum algorithms. For example, Grover's algorithm uses quantum entanglement to search unsorted databases quadratically faster than classical algorithms. By composing these gates into sequences, we can create complex quantum circuits that perform intricate operations on qubits. Quantum circuits are the building blocks of quantum algorithms, enabling us to solve problems that are intractable for classical computers. Measuring a qubit collapses its superposition state, forcing it to assume a definite value of either 0 or 1. The probability of measuring each outcome is determined by the coefficients of the superposition state. This measurement process is essential for extracting information from quantum computations. However, it also presents challenges. When a qubit interacts with its environment, it can lose its quantum properties, a phenomenon known as decoherence. This loss of quantum information happens due to unwanted interactions with surrounding particles, causing the superposition state to collapse prematurely. Decoherence is one of the major obstacles in building large-scale quantum computers, as it limits the stability of quantum computations and the coherence time of qubits. Mitigating decoherence is essential for achieving practical quantum computation. Researchers are actively exploring techniques such as error correction codes and specialized materials to combat decoherence and extend the coherence time of qubits. Shor's algorithm is a quantum algorithm that can efficiently factor integers, which has the potential to break widely used cryptographic schemes like RSA. RSA is a public key crypto system that relies on the difficulty of factoring large numbers. For example, if you wanted to factor the number 15, a classical computer would need to try dividing 15 by all the numbers smaller than it until it found the factors 3 and 5. However, Shor's algorithm can factor 15 much faster by taking advantage of the superposition and entanglement properties of quantum mechanics. This would have profound implications for cybersecurity and require the development of new encryption methods based on quantum-resistant algorithms. Grover's algorithm is a quantum algorithm that can provide a quadratic speedup for searching unsorted databases. Imagine you have a list of 100 names and you want to find a specific name. A classical computer would have to go through each name one by one until it found the correct one. However, Grover's algorithm can find the name much faster by using quantum superposition. This algorithm has applications in various fields, including database searching, optimization, and machine learning. It can accelerate the discovery of new drugs, materials, and other scientific breakthroughs by enabling efficient search through vast data sets. The HHL algorithm is a quantum algorithm that can solve linear systems of equations exponentially faster than classical methods. For example, imagine you have a system of equations describing the flow of traffic in a city. A classical computer would need to solve the system of equations using a method like Gaussian elimination, which can be very time-consuming for large systems. However, the HHL algorithm can solve the same system of equations much faster by leveraging quantum properties like superposition. This could lead to advancements in areas like physics, chemistry, and biology by providing tools for faster and more accurate simulations. The quantum approximate optimization algorithm, or QAOA, is a hybrid quantum classical algorithm that combines quantum computation with classical optimization techniques to tackle combinatorial optimization problems. These problems involve finding the best solution from a vast number of possible configurations. For example, imagine you want to find the shortest route for a delivery truck to visit 10 different locations. A classical computer might need to try all possible routes, which can be very time-consuming for a large number of locations. QOA can solve this problem much faster by using quantum mechanics to find a good solution quickly. Bit flip errors are the simplest type of quantum error, analogous to classical bit flips. Imagine a qubit representing a coin's orientation, heads or tails. A bit flip error would be like accidentally flipping the coin over, changing its state. For example, if a qubit is encoding the value 0 and a bit flip error occurs, the qubit state will change to 1. To correct these errors, quantum error correction employs redundancy, encoding the qubit into multiple physical qubits, like having several copies of the same coin. For instance, a qubit encoding 0 could be encoded into 3 physical qubits, each representing 0. If one of these qubits experiences a bit flip, the majority of the qubits will still represent 0, allowing us to detect and correct the error. By comparing the states of these copies, we can identify and correct any accidental flips. This strategy, known as error detection and correction, is essential for maintaining the integrity of quantum information. Phase flip errors are more subtle and cannot be corrected by simple bit flip techniques. Imagine a qubit representing a spinning coin. A phase flip error would be like changing the direction of the coin's spin without affecting the coin's physical orientation, heads or tails. Consider a qubit in a superposition of 0 and 1. A phase flip error can introduce a negative sign to one of the superposition terms, effectively changing the phase of the superposition. To correct these errors, quantum error correction employs special techniques that target the phase component of the quantum state, ensuring the delicate superposition remains intact. For instance, specialized quantum gates can be applied to the qubit to restore the correct phase, effectively undoing the phase flip error. Stabilizer codes are a powerful class of quantum error correcting codes, utilizing the stabilizer formalism to efficiently represent and manipulate quantum states. These codes provide a systematic approach for designing error correction schemes that can correct both bit flip and phase flip errors. Imagine a group of qubits being protected by a set of rules called stabilizer generators. These rules specify specific combinations of qubit states that are allowed within the protected code space. Any deviation from these rules, indicating the presence of an error, can be detected and corrected by applying appropriate operations to the qubits. Stabilizer codes are like robust frameworks for building quantum error correction mechanisms, offering a structured approach for dealing with various types of quantum errors. They are widely used in practical implementations of quantum error correction, including the development of surface codes. Surface codes are a promising class of topological quantum error correcting codes, offering several advantages for building fault-tolerant quantum computers. They are like robust and adaptable shields protecting the delicate quantum information. They possess high error thresholds, meaning they can effectively correct errors even in the presence of noisy qubits, like a strong armor that can withstand even significant attacks. Their locality property allows for error correction to be performed locally, reducing the complexity of the hardware required for error correction, making them more practical for real-world implementations. Surface codes are implemented on a two-dimensional lattice of qubits, where information is encoded in the topological properties of the lattice. Errors are detected and corrected by measuring the syndrome, which represents the overall state of the lattice. This approach ensures that even if a qubit is corrupted, the information can still be recovered by using the redundant encoding provided by the lattice. Anyons and braiding. Anyons, unlike bosons or fermions, exhibit fractional statistics, meaning their behavior is not fully described by traditional quantum mechanics. These particles can be manipulated by braiding operations, where the order in which they are exchanged affects the final state. For example, in a fractional quantum Hall system, anyons can be braided to form non-trivial topological phases, which can be used for quantum computation. The anyons are created by the interaction of electrons in the system, and their properties are determined by the specific properties of the system. This manipulation of anyons and their braiding operations form the basis for topological quantum computation, offering a fundamentally different approach to quantum information processing. Topological protection. Topological quantum computation relies on encoding quantum information in global topological properties, such as the number of holes in a two-dimensional surface. This makes the information robust against local errors, as these only affect the local properties of the system. The information is protected by the overall topology, which is unaffected by local perturbations. For instance, in a system with anyons, braiding operations can be performed even if some of the anyons are lost or corrupted, as long as the overall braiding pattern remains unchanged. This resilience to local errors is a key advantage of topological quantum computation, particularly when considering the inherent noise and decoherence that plague quantum systems. This inherent robustness is a major advantage over other approaches to quantum computation. Non-abelian anyons. Non-abelian anyons have non-commutative exchange statistics, meaning the order in which they are braided matters, unlike abelian anyons. This non-commutativity allows for the implementation of universal quantum gates, enabling complex quantum computations. In systems with non-abelian anyons, braiding operations can be used to entangle qubits, perform logic operations, and ultimately solve problems intractable for classical computers. The non-abelian nature of these anyons arises from the specific topology of the system, which can be engineered to create a desired set of quantum gates. This type of computation is particularly promising for addressing complex problems in areas like cryptography and material science, physical realizations. Several systems are being explored for implementing topological quantum computation. One promising candidate is the fractional quantum Hall effect, where electrons confined to a two-dimensional plane can exhibit fractional charge and anyonic statistics. Another approach involves Majorana zero modes, exotic quasi-particles that are their own antiparticles, found in topological superconductors. These systems offer the potential for realizing topological qubits that are protected from environmental noise, paving the way for fault-tolerant quantum computation. The fractional quantum Hall effect arises in systems where electrons are subjected to strong magnetic fields, while Majorana zero modes are found in systems with special properties, such as topological superconductors. These physical realizations offer potential pathways for building robust and scalable quantum computers. Challenges and future directions. Despite the promise of topological quantum computation, significant challenges remain in its realization. One key challenge lies in finding suitable physical systems that exhibit robust topological properties and can be manipulated with high fidelity. The development of efficient methods for preparing and controlling anionic states is also crucial. Furthermore, scaling up these systems to support complex computations is a major hurdle. Future research will focus on exploring new materials and platforms, developing sophisticated control techniques, and addressing the fundamental challenges associated with building practical topological quantum computers. The development of new materials and platforms is essential for finding systems that can support topological quantum computation. Sophisticated control techniques are needed to manipulate anyone and perform quantum operations with high fidelity. Addressing the fundamental challenges associated with scaling up these systems will require significant innovation in materials, science, engineering, and quantum control. Quantum information theory extends classical information theory to the quantum domain, providing a framework for understanding the fundamental limits of quantum communication and computation. It explores the unique properties of quantum information, such as superposition and entanglement, to develop new methods for encoding, transmitting, and processing information. This field has led to groundbreaking advancements in quantum computing, cryptography, and communication. Entanglement, a uniquely quantum phenomenon, plays a central role in quantum information theory. It describes a non-classical correlation between two or more quantum systems where their fates are intertwined even when they are physically separated. This interconnectedness allows for tasks impossible in classical physics, such as quantum teleportation and secure key distribution. For instance, the EPR paradox demonstrates how two entangled particles, regardless of their distance, exhibit correlated properties that defy classical explanations. This correlation forms the basis for quantum teleportation, where the quantum state of one particle can be transferred to another, even if they are spatially separated. Another example is quantum cryptography, where entanglement is used to generate secure keys for communication. The security of quantum cryptography relies on the fact that entangled states cannot be cloned, meaning any attempt to intercept the entangled particles will be detected, making it impossible for an eavesdropper to gain access to the secret key. Quantum channel capacity measures the amount of quantum information that can be reliably transmitted through a noisy quantum channel. It involves complex optimization over input states and encodings, taking into account the properties of the channel, such as its noise level and dimensionality. For instance, a noisy qubit channel can transmit a certain amount of information, but the capacity is reduced compared to a noiseless channel. Quantum error correction techniques are crucial for achieving reliable communication over noisy channels. These techniques encode information into redundant quantum states, allowing for the detection and correction of errors introduced by noise. Examples of quantum error correction codes include Shor codes and surface codes, which have been shown to be effective in mitigating noise. The ability to perform quantum error correction is crucial for building large-scale quantum computers, as it allows for the preservation of quantum information despite the presence of noise. Quantum error correction thresholds represent critical noise levels below which arbitrarily long quantum computations can be performed. These thresholds depend on the specific error correction scheme and noise model employed. The error correction threshold is a key parameter for determining the feasibility of building large-scale quantum computers, as it dictates the maximum amount of noise that a quantum system can tolerate while still maintaining reliable computation. Different error correction codes exhibit different thresholds, with some codes offering greater resilience to noise. For instance, surface codes, which use two-dimensional arrays of qubits, have been shown to achieve relatively high thresholds, making them promising candidates for fault-tolerant quantum computation. Surface codes are particularly well suited for topological quantum computation, as they can be implemented in physical systems that exhibit topological order. This means that the information stored in the qubits is encoded in the global properties of the system, rather than in the individual qubits themselves, making it more robust to noise and errors. Surface codes have been shown to achieve thresholds of around 1%, meaning they can tolerate up to 1% error rate in the qubits, while still maintaining reliable quantum computation. Quantum key distribution. Quantum key distribution, or QKD, is a secure way to exchange cryptographic keys between two parties, ensuring their secrecy even in the presence of eavesdroppers. QKD relies on the principles of quantum mechanics, specifically the no-cloning theorem and the uncertainty principle, which prevent an adversary from copying or intercepting the quantum states carrying the key information without introducing detectable errors. This means that any attempt to eavesdrop will leave a trace, alerting the legitimate parties to the presence of an intruder. QKD protocols such as BB84 and B92 utilize photons, which are indivisible particles of light, to transmit key information. These protocols exploit the unique properties of photons, such as their polarization or phase, to establish a shared secret key between two parties. QKD has emerged as a promising solution for secure communication in various applications, including secure communication networks, data encryption, and financial transactions, where the confidentiality and integrity of information are paramount. Post-quantum cryptography. Post-quantum cryptography, or PQC, is a relatively new field that addresses the potential threat posed by quantum computers to existing public key crypto systems such as RSA and ECC, which rely on mathematical problems that are easily solvable by quantum computers. PQC aims to develop cryptographic algorithms that are resistant to attacks by both classical and quantum computers. These algorithms are based on different mathematical problems believed to be intractable for quantum computers, such as lattice problems, multivariate polynomials, and code-based cryptography. These algorithms are designed to provide secure communication and data protection even in the era of quantum computers, ensuring the continued integrity of sensitive information. PQC research is actively advancing, leading to the development of promising candidates for practical implementation, such as the lattice-based cryptography schemes Crystals Kyber and Crystals Dilithium, which have been standardized by NIST, the National Institute of Standards and Technology. Quantum digital signatures. Quantum digital signatures leverage the unique properties of quantum mechanics to provide stronger security guarantees than traditional digital signatures, ensuring the authenticity and integrity of quantum messages. They are based on non-orthogonal quantum states, which are impossible to copy or distinguish perfectly, making it extremely difficult for an adversary to forge a signature. These signatures are particularly important for securing communication and data exchange in quantum networks and other quantum communication systems, where classical cryptographic methods may be vulnerable to quantum attacks. Quantum digital signatures are still under development, but they have the potential to significantly enhance the security of quantum communication and data exchange. Quantum random number generation. Quantum random number generation, or QRNG, exploits the inherent randomness of quantum mechanics to generate truly random numbers for cryptographic applications. Unlike classical random number generators, which often rely on pseudo-random sequences that can be predictable, QRNGs leverage the fundamental unpredictability of quantum measurements to produce truly random and unpredictable numbers. These random numbers are essential for various cryptographic protocols, including key generation, encryption, and secure communication protocols, providing a foundation for robust security. QRNGs have proven their potential for generating high-quality random numbers, finding applications in areas such as secure communication, cryptography, and scientific simulations. Quantum neural networks. Quantum analogs of classical neural networks that utilize superposition and entanglement to learn complex patterns. For example, they can be used to develop more accurate models for identifying and classifying images, such as medical images, and they have the potential to outperform classical neural networks on certain tasks by exploiting quantum properties. Quantum neural networks are being explored for a wide range of applications, including image recognition, natural language processing, and drug discovery. For instance, in medical imaging, quantum neural networks could be trained to detect subtle patterns in medical scans, leading to more accurate diagnoses of diseases like cancer. In natural language processing, they could enhance sentiment analysis and machine translation, enabling more natural and effective communication between humans and machines. In drug discovery, quantum neural networks could accelerate the process of identifying promising drug candidates by analyzing vast databases of molecular structures and predicting their therapeutic properties. Quantum support vector machines, quantum algorithms that extend classical support vector machines, offering potential exponential speed-ups for classification tasks. For instance, these algorithms could be used to efficiently identify patterns in large data sets, such as those found in medical imaging or financial data, and they have the potential to be more efficient than classical algorithms for tasks involving high-dimensional data, such as those found in genomic data or natural language processing. The speed-up comes from the ability of quantum computers to efficiently process vast amounts of data. For example, in financial modeling, quantum support vector machines could help detect anomalies and predict market trends with greater accuracy, leading to more informed investment decisions. In fraud detection, these algorithms could be trained to identify suspicious transactions in real time, protecting individuals and businesses from financial losses. Quantum principal component analysis. Quantum algorithms that perform dimensionality reduction and data analysis, potentially achieving improved scaling properties. These algorithms can be used to extract meaningful insights from large data sets by reducing the number of dimensions without losing critical information. This is especially useful for analyzing data in high-dimensional spaces, such as those found in genomic data or natural language processing. Quantum principal component analysis has the potential to revolutionize data analysis in various fields, enabling the discovery of hidden patterns and relationships that might otherwise be missed. For instance, in genomics research, quantum component analysis could help identify genetic variations associated with specific diseases, paving the way for personalized medicine and targeted therapies. In natural language processing, these algorithms could facilitate the analysis of large corpora of text data, uncovering patterns and insights that could enhance information retrieval and machine translation. Variational quantum algorithms, hybrid quantum classical algorithms for optimization and machine learning tasks, suitable for near-term quantum devices. They combine the power of quantum computers with the efficiency of classical algorithms, enabling the exploration of complex optimization landscapes and the development of more effective machine learning models. These algorithms are particularly promising for applications in areas such as drug discovery, materials science, and financial modeling, where they can provide significant speedups and improved accuracy over classical methods. For example, in drug discovery, variational quantum algorithms could be used to optimize the molecular structures of potential drug candidates, leading to the identification of more effective treatments. In materials science, these algorithms could help design new materials with desired properties, such as increased strength or conductivity. In financial modeling, they could be used to optimize investment portfolios, leading to better risk management and higher returns.